Good morning, students. Now we come to the discussion come to this mean theorem, which is an important theorem from arithmetic function. So here it states that let fn be a multiplicative function, and this is small fn, and let capital Fn is defined to be summation of fd, where d runs over the divisor of n. Then show that this capital Fn is multiplicative if small f is multiplicative. And by multiplicative function, we mean that an arithmetic function f is said to be multiplicative if GCD of f of mn is equal to f of m into f of n whenever GCD of m and n is equal to 1. So with the help of this multiplicative function definition, we are going to show that capital Fn here is called summation of fd, where d runs over the divisor of n is a multiplicative function. So let us see the proof here. So to prove that capital Fn is multiplicative, so we suppose GCD of m and n is equal to 1. Now what we need to show is that to prove f of mn is equal to f of m into f of n. That is, capital F is a multiplicative function. And according to the definition, we have defined summation of f of d. Capital F of n here is called summation of f of d, where d runs over the divisor of n. So if you replace n here by mn, we have f of mn here will be equal summation of f of d, where d runs over the divisor of m and n, with the condition that GCD of mn is equal to 1, means the greatest common divisor among these two is 1 only. So therefore any divisor d of this mn will be of the form d1 d2, where d1 divides m and d2 divides n, and GCD of d1 d2 is equal to 1. Why GCD of d1 d2 is equal to 1? Because the GCD, since GCD of mn is equal to 1. So here we have, now from here, now this f of mn can be written as summation of, what is d here? You replace it by d1 d2, f of d1 d2, where d1 runs over the divisor of m and d2 runs over the divisor of n. But what is f here? Small f. Small f here being a multiplicative function, so small fn. So if you replace n by d also, this f here is a multiplicative function. So this can be written as, instead of f d1 d2, you can write as f of d1 into f of d2, where d runs over the divisor of m and d2 runs over the divisor of n. And the reason is, since f is multiplicative function, therefore f of d1 d2 is same as f of d1 into f of d2, since GCD of d1 d2 is equal to 1. So therefore here you can see that the summation of f d1, where d1 runs over the divisor of m and d2 runs over the divisor of n. So we can write separate summation here. So f of d1, where d1 runs over the divisor of m, into summation of f of d2, where d2 runs over the divisor of n. So what is capital Fn here? We define capital F of n here is called summation of fd, where d runs over the divisor of n. Now if I replace n here by m, what is f of m? Is equal to summation of f of d1. Okay, if I replace d here by d1, then this is summation of f of d1, where d1 runs over the divisor of m. This is same as capital F of m, using this definition of fn here. And this one, f of d2, summation of f d2, where d2 runs over the divisor of n, it is nothing but capital F of n. So this implies that capital F is multiplicative function. I hope it is clear to you how to show that if f being a multiplicative, small f being a multiplicative function, then capital Fn, which is defined as summation of fd, is again a multiplicative function. So next we come to show that, next we prove that tau of n, next theorem or corollary you can say, tau n is multiplicative. We are going to prove this with the help of the above theorem, function. So what we define here, we have, according to definition of tau of n, it stands for the number of divisor of n, and it is defined as summation of 1 where d runs over the divisor of n. So you compare what is capital F n here. It is summation of f of d where d runs over the divisor of n. So if you compare it this, we have f of n here is defined to be 1. You take this tau n as capital Fn and this one here as f of d, or in general we can write f of n. Then if you have here, what we need to show is that this f, small f is small fn equal to 1 is multiplicative. So when you take, suppose GCD of mn is equal to 1. Then f of mn here, which is equal to, f of mn here is defined to be 1. So it will be 1, which can be written as 1 into 1, which is same as f of n into f of m. So this shows that, this implies that small f, that small fn is equal to 1 is multiplicative. Now, which means that this is a multiplicative function. So, and by the preceding theorem, what is that preceding above theorem? Let f be a multiplicative function, then capital Fn, which is defined as summation of fd. In tau n, we define it as, instead of f, we have tau of n, and instead of fd, we have 1. And since the term here, it is a multiplicative function, as we have shown here, Fn is equal to 1 is multiplicative. So, by the above theorem, it shows that f of n, which is called summation of f of d, where d runs over the divisor of n, is equal to summation of 1. Instead of fd, we have 1 where d runs over the divisor of 1, and this summation of 1 is nothing but tau of n is multiplicative. I hope it is clear to you. Next we come to corollary 2, to show that sigma n is multiplicative function. And again, by the preceding theorem, by the theorem that we have stated, what is that? What is sigma n? We define it is summation of fd, the sum of the divisors of n. Where now compare it this, what is that theorem? It is called summation of fd, where d runs over the divisor of n. So where, compare this, what is f of d here, where f of d is equal to d, and this is multiplicative. Why it is multiplicative? This small f is multiplicative since if you take, suppose here, GCD of mn is equal to 1, then f of m is defined as, because f of d is equal to d, so f of m will be m and f of n will be n. So this implies that f of mn will be equal to n into m into n only, which is equal to f of m into f of n. So this implies that f here, fn is multiplicative. So once this function fn in the given theorem, what does it say? If fn is multiplicative, then capital Fn is multiplicative. So here also, by applying that theorem, so we have here f of capital F of n, which is called summation of f of d, where d runs over the divisor of n. This is equal to summation, instead of f of d, you replace it by, what is f of d here? It is equal to d only. So I'll replace it by d, where d runs over the divisor of n. And since this one, because we have defined f here is multiplicative, since this is multiplicative, and this is nothing but sigma n, it is multiplicative. And the reason is by this theorem, if f of n is multiplicative, okay, then capital F of n, which is defined as summation of f of d, where d runs over the divisor of n, is also multiplicative. So by applying this theorem here, because we have shown here d here, that is f of n equal to d is multiplicative here, then by this theorem we can say that sigma n, which is called summation of f of, which is called summation of d, is also a multiplicative function. So therefore sigma n here is multiplicative. I hope it is clear to you.